Hey, welcome! Today we are diving deep into the secret dance between two forces that pretty much run our entire world, electricity and magnetism. You see it happening everywhere, from the simple magnet holding a note on your fridge all the way up to the massive power grid lighting up our cities. So, let's get into it. To get us started, how about a little thought experiment? Picture a regular old bar magnet, North Pole on one end, South on the other. Now, what if you just snap it in half? The two new ends you just made, do they push each other away or do they pull together? Give it a thought. We're going to circle back to this little puzzle once we've uncovered some of the basic rules of the game. All right, so to figure out our puzzle, we've got to first understand what makes a magnet, well, a magnet. And it turns out they follow some really strict and honestly kind of fascinating rules. Now, here's the one rule most of us probably remember from science class. It's the absolute bedrock of magnetism. Like poles repel, and opposite poles attract. A north pole is always going to push another north pole away, but it'll pull a south pole right in. Super simple, but incredibly powerful.
You see, the really crucial point is this. You just can't have one without the other. Every single magnet is what scientists call a magnetic dipole. That just means it always has both a north and a south pole. People have looked, believe me, but a monopole, a magnet that's only north or only south, has never ever been found in nature. They're a package deal.
So let's get back to our little puzzle. When you snap that bar magnet in half, you don't end up with a separate north and south pole. Nope. Instead, you instantly create two brand new, smaller magnets. Each piece immediately grows its own north and south pole. And since you now have a new south pole staring right at a new north pole, they attract each other. And this perfectly illustrates a fundamental law of nature. For every little bit of northness in the universe, there's an equal and opposite bit of southness. You can chop that magnet up into a million tiny pieces, but the total magnetic pole on any object or any piece of it will always add up to zero. Okay, so that explains magnets themselves. But what about how they interact with everyday stuff? Why does a magnet clamp onto a steel fridge door, but completely ignore an aluminum can sitting right next to it? Well, the answer is all about how different materials respond to a magnetic field. Your fridge magnet, that's what we call a hard magnetic material. It's pretty much always magnetic. But your steel fridge door is a soft magnetic material. So when you bring the permanent magnet close, its field temporarily lines up all the little magnetic bits inside the steel and turns the door into a magnet too. And since opposites attract, bam, it sticks. Okay, now things are about to get really interesting. Because some of the most powerful magnets in the world don't look anything like the ones on your fridge. In fact, to get them to work, you have to plug them into the wall. This, right here, is one of the most mind-blowing discoveries in all of physics. It's the first huge clue that electricity and magnetism aren't two separate forces at all. They're deeply fundamentally connected. Anytime you have moving electric charges, which is just what a current is, you create a magnetic field. And that's how we get an electromagnet. You just take a bunch of wire, coil it up, and run a current through it. That flow of electricity generates a powerful magnetic field. And if you wrap that coil around a chunk of iron, you get an incredibly strong magnet that you can turn on and off with the flick of a switch. So we've got electricity creating magnetism. That's pretty cool. But what happens if we flip that idea on its head? Can we run the process in reverse? And this is the question that literally changed the world. If moving charges make a magnetic field, can a moving magnet make charges move? The answer, it turns out, is a huge, resounding yes. And it's the core principle that powers our entire civilization. This amazing effect is called electromagnetic induction. And here's the real trick to it. It's not just any magnetic field that works. It has to be a changing one. When a wire, like a copper wire, feels a magnetic field that's getting stronger or weaker or moving around, that change forces the electrons in the wire to start moving. And that's a current. And we use this principle all the time in a genius device called a transformer. Look at how this works. An alternating current, or AC, flows through one coil of wire. Because it's always changing, it creates a magnetic field that's also always changing. Then you just put a second coil of wire nearby, and that changing magnetic field magically induces a brand new current in that second coil. You're transferring power with no wires even touching. Now, this clever trick of sending power through a magnetic field isn't just a cool party trick. It's the absolute backbone of our entire electrical grid. Let's take a look at how. So, getting electricity from a power plant hundreds of miles away to your house presents a massive problem. If you try to send it using a really high current, you waste a ton of that power just heating up the wires. It's super inefficient. But if you send it at a super high voltage, it's way too dangerous to bring into a neighborhood. So, what do? And the hero of the story is alternating current, or AC. Because AC is constantly flipping back and forth, it's perfect for making those changing magnetic fields that transformers need to work. And since transformers let us change voltage and current on demand, they completely solve our dilemma. Here's the cheat sheet for how it all works. At the power plant, they use a step-up transformer. This cranks the voltage way, way up, which drops the current way down. That's perfect for sending power over long distances without losing much energy. Then, right near your house, on a utility pole, there's a step-down transformer that does the exact opposite. It drops the voltage to a safe level just before it comes into your home. Genius. Okay, so let's bring this all home. We've seen that electricity can create magnets, and magnets can create electricity. What this really means is that they aren't two separate things at all. They're just two sides of the very same fundamental force of nature, electromagnetism. To really let that sink in, let's think about one last question. You've got those giant transmission lines bringing power into your city, right? Okay, what fraction of the actual electrons, the physical charges flowing on those high voltage wires, eventually pass through the device you're using to watch this right now? The answer? Zero. A big, fat 0%. Not a single one. How is that possible? Well, it's because transformers don't transfer charges, they transfer energy. The energy from the electrons moving in the power line gets turned into a magnetic field. That field then jumps the gap to a totally separate circuit in your neighborhood grid and makes the electrons already there start to move. The electrons in your wall have been there the whole time. They're just getting a long-distance push from a magnetic field. It's this incredible, invisible dance happening all around us, all the time. From the tiniest particles to the entire power grid. It's literally what's powering the screen you're looking at, your lights, pretty much your entire modern life. So the only real question left is, knowing this fundamental connection between two of nature's greatest forces, what are we going to power with it next?